Young's modulus and elastic tension. In this application, we are going to calculate the stretched sling band force in pounds, the release velocity of rock in feet per second, and the range of rock if released horizontally 5 feet above ground. So we can start with the Young's modulus E, which is the ratio of stress divided into strain. So we have our equation for Young's modulus E. So we can go here to the left and calculate our cross-sectional area of the hollow tubular latex band of the sling. So that is going to be the outer diameter minus the inner diameter. So you can use pi r squared to solve for both cross-sectional areas and their difference to calculate the effective cross-sectional area. So we calculate 0.06 square inches. We know our Young's modulus is 1000 psi for the latex tubular band. We have our A value. So then our D sub L is the stretched or compressed length with respect to the original length of 8 inches. So L is just the original length of 8 inches in this case. So we just solve for F algebraically by populating the values by substitution. Then you find the reciprocal of the second fraction when we divide fractions. And then we just multiply two fractions out, and then we solve for F. We calculate a value equal to 135 pounds of force. So that would be a really aggressive slingshot band. So if you're able to pull 135 pounds of force, you may have a high performance slingshot. So now we focus on elastic potential energy, and it is described as 1/2 kx squared. So k is the elastic or spring constant, and we'll take this over Newton's force per meters distance. So we'll just convert the force required to stretch the band, convert it to Newton's force, and then the 18-inch straw, we'll convert that to meters distance. So when we divide these out, we get a K constant of 1312.9 newtons per meter, and then X is the actual draw length, so 18 inches again, but converted to meters. So when we substitute these in, we calculate, we substitute 1/2 1312.9 times 0.457 squared, and this will translate to 137.07 joules of potential energy in the stretched sling band. And kinetic energy will equal potential energy, and this is the conservation of energy. Energy can't be created or destroyed, but only changed in form. So we have the total energy transferred from potential to kinetic after the sling is released. And then kinetic energy is 1/2 mass times velocity squared. So we focus on the 2-ounce rock. And so there's 16 ounces to a pound. So 2-ounce rock is 2/16 of a pound, 1/8 of a pound, 0.125 of a pound. So we divide that into 2.2 to get kilograms. So the 2-ounce rock has a mass of 0.05682 kilograms. And so we then substitute the M into the kinetic energy right side component, then multiply times v squared. So then we divide half the mass, multiply times v squared. So we're able to just solve for v by the ratio of 137.07 divided into 0.02841, its square root, to cancel the square. So we calculate a launch velocity of 69.46 meters per second, then times 3.28 to calculate the feet per second. So we approximate it at 228 feet per second release velocity of the rock, the 2-ounce rock. So the last step is to place the slingshot shooter above the ground, horizontal, 5 feet above the ground, and then the rock is released, and then its range is compromised because of gravity. Gravity pulls it down till it hits the ground. So the speed of the rock remains relatively constant. So we can use the delta d sub y equation, the free fall distance equation in kinematics. So it's 1/2 times gravity times t squared. So we can just use metric values. So 5 over 3.28 is equal to 1/2 times 9.81 meters per second squared gravity acceleration times t squared. So then we get 1.524 meters, half of gravity, and then times t squared. So we just algebraically solve for t by finding the ratio of what t squares equals to, and then finding its square root, cancel the square, and then calculate 5.557 seconds of flight time before it hits the ground times the constant velocity of 228 feet per second. So this becomes a range of 127 feet range. So this is an aggressive slingshot, but if you were dealing with a tension force around a normal force of maybe 20 pounds, you could also then make that calculation and a far lower range would occur. And then the Young's modulus could be used in conjunction with the elastic potential energy equation.